Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. When the Indian Ocean tsunami struck on December 26, 2004, it traveled across entire ocean basins at speeds exceeding 500 miles per hour. In less than 15 hours, waves reaching heights of 100 feet devastated coastlines from Indonesia to Somalia, claiming over 230,000 lives. This catastrophe revealed a sobering truth. Our understanding of tsunami science was insufficient to protect the millions of people living in vulnerable coastal communities worldwide. Tsunamis represent one of nature's most destructive forces, yet they remain largely invisible until the moment they strike. Unlike wind-generated waves that rarely exceed 30 feet in height, tsunami waves can tower over 150 feet and carry the energy equivalent of multiple atomic bombs. The physics governing these phenomena involves massive displacement of water, typically triggered by underwater earthquakes, volcanic eruptions, or catastrophic landslides. The science begins with understanding how energy propagates through water. When a submarine earthquake occurs, it displaces enormous volumes of seawater vertically, creating waves that radiate outward in all directions. These waves behave differently from ordinary ocean waves because they involve the entire water column, from seafloor to surface. In deep ocean waters exceeding 12,000 feet, tsunami waves travel at approximately 430 miles per hour while maintaining relatively low heights of just 3 to 6 feet, making them nearly impossible to detect from ships or aircraft. The real danger emerges as these waves approach shallow coastal waters. The phenomenon known as shoaling causes dramatic wave transformation. As the ocean depth decreases, wave speed reduces dramatically, while wave height increases exponentially. A 3-foot wave in deep water can grow to 30 feet or more as it reaches the shore, concentrating its energy into an unstoppable wall of water. Modern tsunami detection relies on sophisticated networks of deep ocean buoys and coastal tide gauges. The National Oceanic and Atmospheric Administration operates the Deep Ocean Assessment and Reporting of Tsunami System, known as DART, which uses bottom pressure recorders to detect the slight pressure changes caused by passing tsunami waves. When sensors detect these pressure anomalies, they transmit data to surface buoys which relay warnings to coastal communities via satellite communication. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. However, traditional warning systems face significant limitations. The time between tsunami generation and coastal impact often provides only minutes to hours for evacuation, depending on proximity to the source. For communities located near earthquake epicenters, warning times may be insufficient for effective evacuation. Additionally, current systems primarily focus on detection and warning rather than active protection of coastal infrastructure. Recent advances in computational fluid dynamics and seismic monitoring have opened new possibilities for tsunami mitigation. Scientists now use advanced modeling techniques to predict wave behavior with unprecedented accuracy, incorporating factors such as seafloor topography, coastal geometry, and urban infrastructure. These models can simulate thousands of potential tsunami scenarios, identifying the most vulnerable areas and optimal protection strategies. The question facing coastal communities worldwide is whether we can move beyond passive warning systems toward active tsunami defense mechanisms. Can we harness our understanding of wave physics, fluid dynamics, and coastal engineering to create barriers that deflect or dissipate tsunami energy before it reaches populated areas? The answer may lie in innovative applications of existing tsunami science, combined with cutting-edge engineering solutions that work with natural processes rather than against them. The fundamental physics governing tsunami behavior reveals both the immense challenge and the potential solutions for coastal protection. Understanding how these waves interact with coastal environments provides the scientific foundation for developing effective defense strategies that could save thousands of lives and billions of dollars in infrastructure damage. Tsunami waves differ fundamentally from wind-generated ocean waves in their wavelength and energy distribution. While typical ocean waves have wavelengths of 100 to 400 feet, tsunami wavelengths can extend from 6 to 60 miles. This enormous wavelength means tsunami waves contain vastly more energy distributed throughout the entire water column rather than concentrated near the surface. When a tsunami wave with a 6-mile wavelength encounters shallow water, the energy compression creates the devastating heights and destructive power witnessed in historical events. The process of wave shoaling follows predictable mathematical relationships that coastal engineers can exploit for protection strategies. As wave speed decreases from 400 miles per hour in deep water to approximately 25 miles per hour in shallow coastal areas, the wave height increases proportionally. This relationship, described by Green's law, indicates that wave height is inversely proportional to the fourth root of water depth. Understanding this mathematical relationship allows engineers to design coastal modifications that can influence wave behavior before maximum energy concentration occurs. Energy dissipation represents the key to effective tsunami defense. Unlike solid barriers that attempt to block waves entirely, successful tsunami protection systems focus on gradually reducing wave energy through controlled dissipation mechanisms. This approach recognizes that trying to stop a tsunami completely is impractical, given the enormous energies involved, equivalent to detonating hundreds of nuclear weapons simultaneously. Friction plays a crucial role in natural tsunami energy dissipation. As waves travel across shallow continental shelves, friction between moving water and the seafloor gradually reduces wave energy. Rough seafloor topography, including coral reefs, rocky outcrops, and artificial structures, increases this frictional energy loss. Coastal vegetation, particularly mangrove forests and dense seagrass beds, also contribute significantly to energy dissipation through drag forces that slow water movement. Wave refraction and diffraction provide additional mechanisms for energy redistribution. When tsunami waves encounter underwater ridges, seamounts, or artificial barriers, they bend and spread, distributing their energy over larger areas and reducing peak wave heights at specific coastal locations. Strategic placement of underwater structures can manipulate these wave physics to protect critical infrastructure, while allowing energy to dissipate harmlessly in less populated areas. The concept of resonance presents both challenges and opportunities. For tsunami protection, coastal bays and harbors can act as resonant chambers, amplifying tsunami waves through constructive interference. The 2011 Tohoku tsunami demonstrated this effect when certain Japanese ports experienced wave heights exceeding 30 feet due to resonant amplification, while nearby areas saw waves of only 10 to 15 feet. Understanding local resonance characteristics allows engineers to design protective measures that prevent harmful wave amplification. Modern computational fluid dynamics enables precise modeling of these complex wave interactions. High-performance computers can simulate tsunami propagation and coastal impact with spatial resolutions of just a few feet, accounting for detailed seafloor topography, coastal geometry, and potential protective structures. These simulations reveal optimal locations and configurations for tsunami defense systems, maximizing protection while minimizing environmental impact and construction costs. The integration of multiple energy dissipation mechanisms offers the most promising approach to tsunami protection. Rather than relying on single solutions, effective defense systems combine offshore energy dissipation, coastal barrier systems, and inland flood management. This layered approach recognizes that some tsunami energy will inevitably reach the shore, requiring comprehensive protection strategies that address multiple scales of the problem. Natural coastal environments have evolved sophisticated defense mechanisms against tsunami impacts over millions of years. These biological and geological systems provide essential insights for developing artificial protection strategies that work in harmony with natural processes rather than disrupting coastal ecosystems. Coral reefs represent nature's most effective tsunami barriers, functioning as massive underwater breakwaters that dissipate wave energy through friction and turbulence. Healthy coral reefs can reduce tsunami wave heights by up to 80%, protecting coastlines far more effectively than most artificial barriers. The complex three-dimensional structure of coral formations creates enormous surface area for energy dissipation, while the shallow water above reefs forces waves to break prematurely, expending their energy in turbulent water rather than reaching the shore intact. The 2004 Indian Ocean tsunami demonstrated the critical importance of coral reef protection. Coastlines protected by healthy reefs experienced significantly less damage than areas where reefs had been degraded by pollution, dynamite fishing, or coastal development. In the Maldives, islands with intact coral barriers suffered minimal damage, while those with degraded reefs faced catastrophic destruction despite being located at similar distances from the tsunami source. Mangrove forests provide another crucial natural defense mechanism, particularly effective in dissipating tsunami energy through their dense root systems and vegetation. These remarkable ecosystems can reduce wave heights by up to 70% over distances of just 100 yards. The complex root structure of mangroves creates enormous drag forces that slow water movement, while the flexible vegetation absorbs wave energy through bending and oscillation rather than rigid resistance. Research following the 2004 tsunami revealed that coastlines protected by mangrove belts wider than 100 yards experienced dramatically reduced casualties and property damage. In Thailand, areas with intact mangrove forests reported death tolls nearly 90% lower than adjacent areas where mangroves had been cleared for shrimp farming or coastal development. This natural protection came at zero construction cost and provided additional benefits including carbon sequestration, fisheries habitat, and coastal erosion prevention. Seagrass meadows contribute to tsunami protection through their ability to create drag forces that slow water movement and trap sediments that could otherwise become dangerous projectiles. These underwater grasslands can reduce wave energy by up to 40%, while providing critical habitat for marine species and improving water quality through nutrient filtration. Unlike coral reefs, seagrass systems can be established relatively quickly and are highly adaptable to various coastal conditions. Coastal dunes and barrier islands represent geological tsunami defenses that dissipate energy through controlled overtopping and infiltration. Well-designed dune systems allow some water to pass through or over them, reducing pressure that could cause catastrophic barrier failure. The porous nature of sandy barriers enables water infiltration that dissipates energy, while the dune vegetation provides additional drag forces and structural stability. The Netherlands has pioneered the integration of natural coastal defense systems with engineering solutions through their innovative building with nature approach. This strategy uses natural processes to enhance coastal protection while maintaining ecosystem services. Projects include artificial reef construction that mimics natural coral formations, strategic sediment placement that supports dune formation, and wetland restoration that provides flood protection while creating valuable habitat. Recent advances in biomimetic engineering enable the creation of artificial structures that replicate the energy dissipation mechanisms of natural systems. Artificial reefs constructed from specially designed concrete modules can provide tsunami protection while supporting marine ecosystems. These structures incorporate complex surface textures and internal chambers that maximize energy dissipation through turbulence generation and wave interference. Living shoreline technologies combine natural and artificial elements to create adaptive coastal defense systems. These approaches use native vegetation, sustainable materials, and natural coastal processes to provide protection that improves over time as ecosystems establish and mature. Unlike rigid seawalls that can fail catastrophically, living shorelines provide flexible protection that adapts to changing conditions while supporting biodiversity. The economic benefits of nature-based tsunami protection are substantial. Healthy coral reefs provide coastal protection services valued at over $900 billion annually worldwide, while mangrove forests offer protection worth over $65 billion per year. These natural systems provide protection at a fraction of the cost of artificial barriers while delivering additional ecosystem services, including fisheries support, tourism revenue, and climate regulation. Modern coastal engineering has developed sophisticated artificial defense systems that harness tsunami science to protect vulnerable communities. These technological solutions combine advanced materials, science, structural engineering, and wave physics to create barriers that can withstand the enormous forces generated by tsunami waves while minimizing environmental impact. Offshore breakwater systems represent the most promising approach for large-scale tsunami protection. These massive underwater structures are positioned miles from shore in water depths of 100 to 300 feet, where they can dissipate tsunami energy before waves reach maximum height through shoaling. Unlike traditional coastal barriers, offshore breakwaters work by forcing waves to break in deep water, converting their organized energy into turbulent dissipation that dramatically reduces wave heights reaching the shore. The engineering challenges of offshore tsunami barriers are immense. These structures must withstand water pressures exceeding 5,000 pounds per square foot, while remaining stable in seafloor conditions that may include soft sediments, seismic activity, and strong ocean currents. Advanced materials, including ultra-high-performance concrete, fiber-reinforced polymers, and specially designed steel alloys provide the strength and durability required for these extreme environments. Floating breakwater technology offers a flexible alternative to fixed offshore barriers. These systems use interconnected floating modules anchored to the seafloor through tensioned cables and dynamic positioning systems. During normal conditions, floating breakwaters remain submerged and invisible, minimizing impact on marine navigation and ecosystems. When tsunami waves approach, the barriers automatically adjust their position and orientation to maximize energy dissipation while maintaining structural integrity. Japanese researchers have developed innovative tsunami barrier walls that can be deployed rapidly in response to earthquake warnings. These systems use hydraulic mechanisms to raise protective barriers from underground chambers within minutes of seismic detection. The barriers incorporate shock-absorbing materials and flexible joints that allow them to bend rather than break under extreme wave forces. Advanced sensor networks monitor structural stress in real time, enabling dynamic adjustments to barrier configuration based on incoming wave characteristics. Permeable barrier technology represents a paradigm shift in tsunami protection design. Rather than attempting to block waves completely, these systems allow controlled water passage while dissipating energy through turbulence generation and flow restriction. Perforated concrete walls, steel mesh barriers, and specially designed rock formations create pressure differences that break up wave structure and reduce peak velocities. This approach prevents the dangerous pressure buildup that can cause catastrophic barrier failure. Wave energy conversion systems offer the possibility of turning tsunami threats into beneficial energy resources. These technologies capture the kinetic energy of moving water and convert it to electricity through turbines, oscillating water columns, or pressure-activated generators. While not eliminating tsunami danger entirely, energy conversion systems can reduce wave energy by 20 to 30% while generating power that supports coastal communities during post-disaster recovery periods. Smart barrier systems integrate artificial intelligence and real-time monitoring to optimize tsunami protection dynamically. These systems use networks of pressure sensors, wave height monitors, and seismic detectors to predict incoming wave characteristics and adjust barrier configurations accordingly. Machine learning algorithms analyze historical tsunami data and current ocean conditions to determine optimal protection strategies for specific wave scenarios. Modular barrier construction enables rapid deployment and adaptive protection strategies. Standardized barrier components can be manufactured in controlled factory environments and transported to coastal areas for assembly. This approach reduces construction time from years to months while ensuring consistent quality and performance. Modular systems also enable communities to expand protection gradually as resources become available, rather than requiring massive upfront investments. The integration of tsunami barriers with renewable energy infrastructure creates synergistic benefits for coastal communities. Offshore wind turbines can be designed with tsunami-resistant foundations that provide additional wave energy dissipation. Solar panel installations on barrier structures generate clean electricity while serving protective functions. These integrated approaches reduce the overall cost of tsunami protection while supporting sustainable development goals. Advanced numerical modeling enables precise optimization of barrier design for specific coastal environments. Computational. Fluid dynamics simulations can test thousands of barrier configurations, identifying optimal shapes, sizes, and positions for maximum protection effectiveness. These models account for local seafloor topography, typical wave conditions, and potential tsunami sources to create customized protection solutions for each coastal community. The economic feasibility of engineered tsunami protection systems depends on accurate cost-benefit analysis that considers both direct protection benefits and indirect economic impacts. Modern barrier systems typically cost between $50 to $200 million per mile of protected coastline, but can prevent billions of dollars in tsunami damage while supporting ongoing economic activity in protected areas. Real-world implementation of tsunami protection systems provides valuable insights into effective strategies for coastal defense. Examining successful projects from Japan, the Netherlands, Indonesia, and other vulnerable regions reveals the practical challenges and proven solutions for large-scale tsunami mitigation efforts. Japan's comprehensive tsunami protection system represents the world's most extensive coastal defense network, developed through decades of experience with devastating tsunamis. Following the catastrophic Meiji Sanriku tsunami of 1896, Japan began constructing massive seawalls along vulnerable coastlines. The Taro seawall in Iwate Prefecture, completed in 1967, stands 34 feet high and extends over a mile along the coast. This structure successfully protected the town of Taro during the 1960 Chile tsunami, demonstrating the effectiveness of properly designed coastal barriers. However, the 2011 Tohoku earthquake and tsunami revealed critical limitations in Japan's protection strategy. Despite having the world's most extensive seawall network, many barriers were overtopped by waves exceeding 40 feet in height. The failure of the Fukushima Daiichi nuclear power plant's seawalls led to reactor meltdowns and radioactive contamination, highlighting the catastrophic consequences of inadequate protection design. These events prompted Japan to develop new approaches, combining multiple protection layers rather than relying solely on seawalls. Japan's post-Tohoku reconstruction efforts emphasize build back better principles that integrate natural and artificial protection systems. The Miracle Pine project in Rikuzen-Takata combined seawall reconstruction with forest restoration, creating layered defense systems that provide both protection and environmental benefits. New barrier designs incorporate flexible materials and controlled overflow systems that prevent catastrophic failure while maintaining protection effectiveness. The Netherlands Delta Works project demonstrates successful integration of storm, surge and tsunami protection with sustainable development goals. This massive engineering undertaking, completed over 30 years, created a network of barriers, dams, and surge barriers that protect 2/3 of the Dutch population from flooding. The Oosterschelde Kering storm surge barrier combines massive concrete pillars with movable gates that can be closed during extreme weather events while maintaining normal tidal flow for marine ecosystems. Dutch engineers pioneered the concept of living with water rather than fighting against it. The Room for the River program deliberately allows controlled flooding in designated areas during extreme events, reducing pressure on critical infrastructure and populated areas. This approach recognizes that complete flood prevention is impossible and focuses on managing water flow to minimize damage while maintaining ecosystem functions. Indonesia's post-2004 tsunami reconstruction efforts demonstrate the importance of community-based protection strategies. The Aceh Province Reconstruction Program combined traditional knowledge with modern engineering to create culturally appropriate protection systems. local communities participated in designing evacuation routes, early warning systems, and land use. Planning that incorporated indigenous understanding of coastal hazards. The Indonesian approach emphasized education and preparedness alongside physical infrastructure. Community-based early warning systems use traditional communication methods combined with modern technology to ensure rapid information dissemination. Schools and public buildings were relocated to higher ground or constructed as vertical evacuation centers that can accommodate entire communities during tsunami events. Thailand's integrated coastal management approach, following the 2004 tsunami, combines mangrove restoration with engineered protection systems. The Andaman Seacoast Restoration Project replanted over 20,000 acres of mangrove forests while constructing selective barriers in critical areas. This hybrid approach provides natural protection that improves over time while maintaining tourism and fishing activities essential to local economies. Chile's tsunami preparedness system, developed after experiencing numerous historical tsunamis, emphasizes rapid evacuation over protective barriers. The country's geography, with narrow coastal plains backed by steep mountains, enables vertical evacuation strategies that move people to safety within minutes. Comprehensive education programs ensure that coastal residents understand tsunami risks and evacuation procedures, reducing reliance on expensive infrastructure. The success of global tsunami protection efforts depends heavily on international cooperation and knowledge sharing. The Indian Ocean Tsunami Warning System, established after the 2004 disaster, demonstrates effective regional collaboration in hazard monitoring and early warning. This system provides consistent tsunami alerts across 28 countries, enabling coordinated response efforts and information sharing about effective protection strategies. Financing mechanisms for tsunami protection infrastructure require innovative approaches that spread costs across multiple stakeholders and time periods. Japan's reconstruction financing combined government resources, international aid, and private sector investment through public-private partnerships. Insurance systems that provide premium reductions for communities with certified protection. Systems create economic incentives for proactive investment in tsunami defense. Long-term maintenance and system upgrades represent critical factors in protection system effectiveness. Japan's experience shows that barriers require continuous monitoring, repair, and enhancement to maintain protection capabilities. Climate change impacts, including sea level rise and changing storm patterns, necessitate adaptive management approaches that can modify protection systems as conditions evolve. The most effective tsunami protection strategies combine advanced engineering solutions with comprehensive community preparedness programs and sophisticated early warning systems. This integrated approach recognizes that physical barriers alone cannot guarantee complete safety, and that human behavior and social organization play crucial roles in minimizing tsunami casualties and damage. Modern early warning systems represent technological marvels that can detect tsunami generation within minutes of earthquake occurrence. The Pacific Tsunami Warning Center operates a global network of over 150 seismic monitoring stations that continuously track earthquake activity worldwide. When sensors detect earthquakes exceeding magnitude 6.5 in underwater, locations automated systems immediately begin calculating potential tsunami generation and propagation patterns. Advanced seismic analysis techniques enable rapid discrimination between tsunami-generating and non-tsunami earthquakes. Scientists analyze factors including earthquake magnitude, depth, duration, and fault mechanism to determine tsunami risk within 10 to 15 minutes of occurrence. Artificial intelligence systems trained on historical earthquake and tsunami data can predict wave characteristics with increasing accuracy, providing more precise warnings that reduce false alarms while ensuring adequate response time. Deep ocean detection systems provide crucial confirmation of tsunami generation and real-time wave monitoring. The expanded DART network includes over 60 deep ocean stations that detect passing tsunami waves and transmit measurements via satellite communication. These systems measure wave height, period, and propagation speed, enabling scientists to refine predictions and provide updated warnings as waves approach coastal areas. Integration of warning systems with automated infrastructure response creates seamless protection activation. In Japan, earthquake detection networks automatically trigger tsunami barrier deployment, traffic signal coordination for evacuation routes, and emergency broadcast systems within seconds of seismic detection. Smart city technologies enable coordinated response across multiple systems, optimizing evacuation efficiency while activating physical protection measures. Community education programs represent the foundation of effective tsunami preparedness, ensuring that residents understand risks and know appropriate response actions. Successful programs combine traditional educational approaches with innovative technologies, including virtual reality tsunami simulations, mobile applications with GPS-enabled evacuation guidance, and community-based preparedness exercises that practice real-world scenarios. The Tsunami Ready certification program, developed by the National Weather Service, provides communities with standardized criteria for tsunami preparedness. Certified communities must demonstrate adequate warning systems, evacuation plans, public education programs, and emergency response capabilities. This certification creates incentives for comprehensive preparedness while providing residents with confidence in local protection measures. Social media and mobile communication technologies enable rapid information dissemination and coordinated community response. Emergency management agencies use multiple communication channels, including traditional broadcast media, social media platforms, wireless emergency alerts, and dedicated emergency communication applications. Redundant communication systems ensure that warnings reach residents even if primary systems fail due to earthquake damage or power outages. Evacuation route planning requires sophisticated modeling that accounts for population distribution, traffic patterns, and potential infrastructure damage. Advanced simulation software models, evacuation scenarios under various conditions, identifying optimal routes and potential bottlenecks that could delay escape. Dynamic traffic management systems can redirect vehicles and pedestrians in real time, based on current conditions and evacuation progress. Vertical evacuation strategies provide protection options for areas where horizontal evacuation is impractical due to geography or insufficient time. Specially designed tsunami evacuation buildings combine normal community functions with emergency shelter capacity, including reinforced construction, elevated safe areas, and emergency supplies. These structures serve schools, community centers, or commercial buildings during normal times, while providing life-saving shelter during tsunamis. Cultural sensitivity in preparedness programs ensures that protection strategies respect local traditions and social structures. Indigenous communities often possess traditional knowledge about tsunami risks and natural warning signs that complement modern scientific monitoring. Successful programs integrate traditional wisdom with contemporary technology, creating culturally appropriate response strategies that benefit from both knowledge systems. Economic incentives for community preparedness include insurance premium reductions, tax benefits for certified tsunami-ready properties, and economic development preferences for communities with comprehensive protection systems. These incentives recognize that individual and community preparedness investments benefit society broadly by reducing disaster response costs and economic disruption. Regular preparedness exercises and drills maintain community readiness while identifying areas for improvement in protection systems. Large-scale exercises involving thousands of participants test both technological systems and human response capabilities under realistic conditions. Post-exercise evaluations identify weaknesses in warning systems, evacuation procedures, or community coordination that require attention before actual events occur. International cooperation in tsunami preparedness includes technology sharing, joint training programs, and coordinated response protocols that enable mutual assistance during major events. Regional organizations facilitate knowledge exchange between countries facing similar tsunami risks, enabling adaptation of successful strategies to local conditions while avoiding duplication of expensive research and development efforts. The next generation of tsunami protection systems will integrate artificial intelligence, advanced materials science, and adaptive technologies to create dynamic defense networks that can respond to changing conditions and emerging threats. These innovations promise more effective protection at lower costs while addressing the evolving challenges posed by climate change and increasing coastal development. Artificial intelligence represents a revolutionary advance in tsunami prediction and response capabilities. Machine learning algorithms trained on vast datasets of historical earthquakes, ocean conditions, and tsunami events can identify subtle patterns that escape human analysis. These systems can predict tsunami characteristics with unprecedented accuracy, distinguishing between different types of seismic events and their potential for tsunami generation within minutes of occurrence. Advanced AI systems integrate real-time data from multiple sources, including seismic networks, ocean buoys, satellite imagery, and coastal sensors, to create comprehensive situational awareness. Deep learning algorithms continuously refine their predictions based on new data, improving accuracy over time while reducing false alarm rates that can desensitize communities to genuine threats. Natural language processing enables automated generation of customized warnings for different communities based on local risk levels and response capabilities. Autonomous underwater vehicles equipped with sophisticated sensors provide mobile tsunami monitoring capabilities that complement fixed detection systems. These robotic platforms can be deployed rapidly to areas of suspected tsunami generation, providing direct measurements of wave conditions and seafloor changes that might indicate ongoing seismic activity. Swarms of coordinated underwater drones can create temporary monitoring networks that track tsunami propagation with unprecedented spatial and temporal resolution. Smart materials technology enables the development of adaptive protection structures that modify their properties in response to changing conditions. Shape memory alloys can alter barrier configurations automatically based on wave characteristics, while self-healing concrete contains embedded healing agents that repair minor damage without human intervention. Flexible composite materials provide structural strength while allowing controlled deformation that dissipates energy without catastrophic failure. Biomimetic engineering continues to unlock new possibilities for tsunami protection inspired by natural systems. Researchers are developing artificial kelp forests that mimic the energy dissipation characteristics of natural seaweed while providing enhanced durability and controllable properties. Synthetic coral structures incorporate advanced materials and internal cavities that maximize energy dissipation while supporting marine ecosystems through integrated habitat features. Nanotechnology applications in tsunami protection include self-monitoring concrete that contains embedded sensors capable of detecting structural stress, crack formation, and material degradation at the molecular level. These smart materials can communicate their condition wirelessly, enabling predictive maintenance that prevents structural failure before it occurs. Nanoparticle-enhanced materials provide superior strength-to-weight ratios, enabling construction of lighter barriers that require less massive foundations. Digital twin technology creates virtual replicas of coastal protection systems that enable continuous monitoring, optimization, and predictive maintenance. These computer models incorporate real-time sensor data to simulate system performance under various conditions, identifying potential weaknesses and optimization opportunities. Digital twins enable testing of proposed modifications or new protection strategies without risking actual infrastructure or coastal communities. Climate adaptation strategies address the increasing challenges posed by sea level rise, changing storm patterns, and coastal erosion that affect tsunami protection effectiveness. Future protection systems incorporate adaptive management approaches that can be modified as environmental conditions change. Modular construction techniques enable incremental system enhancement, while floating and amphibious structures provide protection that adapts to changing water levels. Space-based monitoring systems using constellations of small satellites provide global tsunami detection capabilities that complement ground-based networks. Advanced radar and optical sensors can detect ocean surface changes associated with tsunami waves while monitoring coastal conditions that affect protection system performance. Satellite communication networks ensure reliable warning dissemination, even when terrestrial infrastructure is damaged by earthquakes or other disasters. Quantum computing applications in tsunami science promise dramatic improvements in wave modeling and prediction capabilities. Quantum algorithms can solve complex, fluid dynamics equations that describe tsunami behavior with unprecedented speed and accuracy. These computational advances enable real-time modeling of tsunami propagation that accounts for detailed ocean topography, coastal geometry, and infrastructure interactions. Community resilience technologies focus on rapid recovery capabilities that enable coastal communities to return to normal operations quickly after tsunami events. Modular infrastructure systems can be deployed rapidly to replace damaged facilities, while advanced materials enable construction of more resilient buildings and utilities. Distributed energy systems, including microgrids and renewable energy sources, maintain critical services during recovery periods. The integration of these emerging technologies will create comprehensive tsunami defense networks that provide multi-layered protection through coordinated systems of detection, warning, physical barriers, and community response. These integrated approaches recognize that complete tsunami elimination is impossible, focusing instead on damage minimization and rapid recovery capabilities that enable coastal communities to thrive despite natural hazards. Future tsunami protection. Investments will increasingly emphasize cost-effectiveness, environmental sustainability, and social equity to ensure that protection benefits reach all coastal communities regardless of economic status. International cooperation and technology transfer programs will accelerate the deployment of advanced protection technologies to vulnerable regions worldwide, creating a global network of tsunami-resilient coastal communities.